Okay, so let's start. And since I a little bit ran out of time last time, I would just want to point you all to kind of a page of resources that I accumulated and put on my GitHub page. I put it already last week on Slack, and here I just want to point out a couple of resources that I highly recommend for anybody who wants to go deeper into the topic of RNNs and LSTMs. And I thought, let's get this done now, not that we run out of time and I don't get to it again. Definitely what I want to recommend is the 2016 lecture. This is actually from the Stanford Computer Vision class led by Andrei Karpathy. It's amazing. I think this is the best explanation of RNNs, and the use case is image captioning. So input is an image and you want to describe with natural language what is actually on that image. Really clear explanations. Then there's a lot of great TWIML content, actually great podcasts like here, Richard Socher at Salesforce, chief scientist at Salesforce, shows like what language models can be applied to apart from text. And of course with Jürgen Schmidhuber on LSTMs. It's a very, very good podcast as well that I recommend. With the notebooks, I think the fast AI stuff is great, and I think many in the class or in the study group also went already through the fast AI NLP course study group, so most of you will be aware of this. If not, check it out. And some blog posts, actually we will look into some of them today, so let's not go through that. Then there are also official PyTorch and TensorFlow tutorials and some papers. I wanna especially point out, I think this one here, the SHA-RNN. I think Joseph, you posted it recently into the Slack community, I think. And it's actually a paper by Stephen Meredy that actually shows how to train very efficient RNN models with single head attention. And they perform similar on some tasks to transformers. And he kind of makes the point that while most of the state-of-the-art results nowadays are made with transformers, one reason for that could also be that at this time, it looks like that in the NLP community, RNNs are understudied, and we are not really like using them to their full potential. So they are not completely, let's say, out of fashion, and we are not learning anything unuseful here. Exactly, and here just some little toy where you can write your own texts with transformer models, and I think it was one of the first like successes of Hugging Face, where really the community became aware of this new player. All right, so check it out. And yeah, exactly. So before we dive into the charts, I just want to give a little bit more motivation for language models that I couldn't do last time, because what was shown were really the text examples from the window RNN and generated by these n-gram RNNs, and then by the RNN-based language models. And the texts were somehow showed some like coherence, but still were not really like convincing. But then, the transformer architecture came along. I will not go in it at all. I just want to touch on the topic of language models and how powerful they can become. And then GPT-2 came along, right? Released by OpenAI. Probably all of you will be aware of it. And the texts it creates, here are some examples on the page, on the like blog post that accompanies it. Actually, they are simply amazingly coherent and could really trick somebody just reading this into believing this has been written by humans. And that, of course, then justifies definitely the whole staged release process that they did, being convinced a little bit that it could potentially lead to harmful usage, being able to generate this amount of fake text, just by an algorithm. And just a couple of weeks ago, they actually just went with that even further and trained an even larger model. I think GPT-2 was about maybe 15 million parameters, or wait a second, I don't know, 1 billion parameters. And then a couple of weeks ago, they released completely new model, GPT-3 with 175 billion parameters. So it's huge, it's larger than any language model before. And just what I want to show here is basically the main message of the paper, it's actually quite long paper, 74 pages, is that you can solve, or that the goal is to solve all kinds of NLP tasks just by using language models. So this model was only trained in language model style, and I think also autoregressive, like that means predicting the next word from left to right. And then they do just zero-shot inference. This means you describe a task and give a word. And the model does not see any like training data on translation, and then it's supposed to translate it. Then what they call one-shot is also basically just inference, because you don't really update any gradients. You just give actually the model the task description and then an example, and then it should complete it again. But this is not leading to any gradient updates. And few-shot, where you give a couple more examples. And it actually led to like very amazing results that you got without actually training an explicit language translation model. You got not state of the art, but a pretty good translation model. And that's quite impressive, given that it has never been trained on translation. Exactly. So language modeling is powerful. And I think
just a quick question on there's a 1.9 billion parameters. What are these? Are these like a embedding metrics for each word in a different context? Is that these 1.9 billion parameters are made up of, or is something else?
It's the whole model. It's not just embeddings. It's like all the hidden states within the transformer architecture. As I said, we're not going to look into that today, where there will be several lectures on that afterwards. But it's basically you have linear layers in there. You have embeddings definitely, but I think most of the layers are linear layers, hidden states, and the full size is actually 175 billion parameters. Yeah. Of course, there can be a debate on how practical that is, because I don't know how many GPUs you need to fit that model on. But yeah, it has 96 layers. I think this is also the largest transformer model that has ever been trained.
Yeah, that was going to be my next question, actually. Like, how easy is it for people to use this on like simple like Colab or something like a GPT-3 with such huge parameters?
Yeah, I guess that's impossible.
Yeah.
Like on the just user GPU, it's impossible. And yeah, but I think the main goal, yeah.
So that's probably Hugging Face is doing all this clipping and then all the quantization just to trim it to a level where we can use on the single GPU or small enough computing power, I guess.
Exactly. So also through distillation or something like this to make it more usable, actually, because as like this, the typical data scientist without actually a huge data center cannot train a model like this. Yep. Okay, that was just some motivation, and now let's get into the Stanford lecture today. LSTMs, basically, or the topic is vanishing gradients and fancy RNNs, which are LSTMs and GRUs. But if you agree, because we rushed last time a little bit through the backpropagation part, so if you agree, I would just go through these 3 slides of the RNN lecture, or are you saying that not necessary, let's just move on with LSTMs?
Go for it.
I think some revision would be good.
Okay, good. I'm not going to revise the whole lecture because I think otherwise we will not move on, but just the backprop part, because actually the lecture today, it starts off quite tough, I would say, with actually a lot of math and backpropagation. Then it becomes a little bit more intuitive with the architectures, and then actually it fades out quite nicely. But we have to go through some quite hard, tough stuff in the beginning. Okay, so backpropagation in RNNs. These are our sequential time steps with our weight matrices or our weight matrix repeatedly applied. In the end, we're calculating some loss. And then the question is, how do we actually calculate the gradients for this RNN, for the sequential structure, right? And exactly, so what's the derivative of the loss JT with respect to a repeated weight matrix? Because remember, it's the same matrix, it's just being repeated all over again. And the solution is that actually the gradient with respect to a repeated weight matrix is the sum of the gradients, of the sum of the gradient with respect to each time it appears. And this you see in this equation, actually. The loss with respect to the weight matrix is, this is the sum over the loss of the gradient of the loss with respect to each time it appears, by looping through just the time steps I here. And the proof follows from the multivariable chain rule, which says that if I have a function f of x of t and y of t, and I want to get the derivative of function f with respect to t, I'm actually calculating I'm applying the chain rule separately along these paths. Actually, do you see my cursor?
Yes.
Yes.
Okay, good. So you apply the chain rule along these paths, and then you add them up, right? So you have the derivative of f with respect to function x, and since x is a function of t, you have you multiply that by the derivative of x with respect to t, and then you sum. And you do the same for y, and you sum them up. And in the case of RNNs, we can see them actually in the same scheme, just given that all of our these are the weight matrix W, sorry, applied at each time step t. Yeah, and you can see and you can see we ultimately will just want the gradient of the loss with respect to the repeated weight matrix, but it's repeated these many time steps, and you can actually see that there is a function between these between the individual time step this matrix is applied and the, let's say, overall time independent matrix, which is just equality. Yeah, and then you apply the same rule here and add up the derivative of the loss with respect to the weight matrix at time step I, and then you take the derivative of the weight matrix at step I with respect to the weight matrix. And since these are actually the same, because the same matrix is applied at each step, this is 1, and then we are ending up simply at this equation that we started with. Yeah, exactly. And then so how you calculate this? You calculate it backwards, as usual in backpropagation. Let's say that the special part in RNNs is that you actually calculate it back through. It's called backpropagation through time, because here we said this is actually our time component, our sequential steps, and since we're going from here, and first we calculate the derivative of the loss with respect to the last time step t. Then we calculate the derivative of the loss with respect to weight matrix at time step t minus 1. And we also calculate them and so on. And it's important just to note that you calculate it in terms of each other. So you use the result from here to calculate this gradient and go back like this, just for efficiency reasons. And finally, as we said last time, and we discussed this a lot actually, this process, backpropagation process, is carried out through a batch, not throughout the entire corpus of data that you have, but just through one batch of data. Then you update your weight matrix, and then you move on to the next batch. Yeah, I think that was it for the revision. Any questions so far?
So the function at each time step, does that include the hidden state, or is it just the weight matrices at each step?
Yeah, actually, it includes the hidden state, because to get to your weight matrix, you need to backpropagate through the hidden state.
Okay.
Yeah. So there are like a lot more details to it, right? This is again just an simplified view, but I think if you open up that box, we will spend the whole time discussing it and maybe not even figuring it out. Yeah.
So my question is that doesn't this value of h of I with respect to time keep changing? Because every time you make a pass, the weight values will change.
Mm-hmm.
That's the question. Like at each step, actually, it's a hidden state that is changing. The weight matrix remains same.
Yep.
So that's why we include the hidden state.
For the back propagation, the weight matrix supposed to change on every stage, every hidden stage. So when on every, that's my understanding at least.
Okay. Well, I think how it is. You calculate the gradients. So it's like you calculate your gradients, right? And then you have your gradients, and then you apply the step. And then the weights change. The one weight matrix you have, they change, and then you move on to the next batch. But I think maybe if the question was if the weight matrix is changing during the calculation of gradients, and my answer is I do not think so.
No, that's correct. I think you're right, Stefan. The weight matrix is updated after each back propagation step, and then it's applied to the entire. It's applied to the entire RNN in the next forward pass. The updated weight matrix, the same one, is applied at every step, and then you go back. You do your back propagation again. You arrive at the all of the derivatives, and then you update the weight matrix again, and so on. So yeah, the weight matrix is changing. But every time it changes, it's applied through all the RNN, the entire RNN. It's the same weight matrix.
Mm. Yep.
Yeah. So, but it's the same weight matrix, but the changes are going to, let's say, if you say H0 to HT minus 1. So weight matrix, when we are doing a back propagation, each time the same weight matrix, but it will be changing multiple times because we are calculating grading on each hidden stage. So when it reach from HT to all the way to back H0, the same weight matrix WH has been changed, let's say here HT minus 1 times. Is that correct?
I don't think so, because you calculate you don't change the weights while you're calculating the gradients, yeah? So you first calculate your gradients, and the gradients at each time step will be different, but then you sum them up to get your overall gradient, yeah?
Okay.
And then you perform the weight update.
Yeah, it's added is, yeah, I think I got it. Okay, yeah, it's the added weights, because it's the same weight matrix. So you all add all the gradients and apply just once. Why would you just keep on doing it? Yeah,
exactly.
Yeah,
good. But the weight matrix on stage HT minus 3 is not the same weight matrix as HT minus 1. The values have changed, right?
No, they haven't.
Yeah, they haven't.
Well, why did you go through all the
your gradients change. So, okay, let's make it once more. During forward propagation, your weights stay the same, but your hidden state changes. The values in your hidden states, they change. Yeah, you modify these during forward propagation.
Okay.
Then you compare whatever output you have to your ground truth. You get the loss, and then you back propagate step by step. And during this, what changes is you get a gradient for each time step. Yeah. And these gradients for each time, the gradient for each time step is different, yeah. But then you sum them up.
Why would it be different though? If the weights are the same at HT minus 1 versus HT minus 3?
Because, for example,
hidden states are different.
Because you have a word here, yeah. For example, here at T minus 3 that has been encoded, but encoded in a very bad way. Okay. And you actually, then calculate your output, you get a loss, and in this loss, it's reflected that this step or here somehow in this transformation, we made a mistake, and therefore you want to update this. But if you got something right, you don't want to update it. So the gradients will be different at each time step, but then you sum them up in the end anyway.
So during the next batch of forward propagation, you change the hidden states, not the weights?
Yes, you calculate the hidden states. They are calculated using the same weight matrix all over again.
Got it.
Yeah. All right.
Just no question before you move on.
Okay.
I know this hidden stage is nothing but it's just a vector, which keep on changing on every stage. But what exactly is it's some sort of like again it's some sort of weights, but I'm not getting the point what exactly it is. It's a vector.
The hidden
It's
state.
a random vector.
The hidden state.
Yeah.
Yeah, the hidden state are not weights. It's activations. And the difference between weights and activations is, it's like, as Jeremy from FastAI always puts it, weights are learned. So these weight matrices are learned and updated with gradient descent and backpropagation. And activations that form this hidden state are calculated. Okay, so you calculate your activations using your weights, but they are not learned.
Another way to think of it is that the hidden states are intermediate values which depends on the data, but the weights should actually become stable at the end of all your calculations and hold good for other calculations, at least some of the time.
Okay.
Yeah, that they should converge theoretically. Yeah, I guess.
Intuitively, in this particular instance, the hidden states are contextual representation of your words in the context of the batch that you just processed.
Yep.
Okay.
If I can follow up with that question. So let's say the big metrics WH. So during backprop, the weights are updated, but we can think between every hidden state and the prior hidden state that not all the weights of WH are updated, just some of them. And then the next step, then some other words gets updated and then some others. Is right? Do you agree with that, Steph, or?
No, because
Go ahead.
Yeah, I mean, like we discussed earlier, the weights are not changing until the end because we change all of them together by summing and taking the derivative. At each step, you're just calculating that specific gradient for that time step.
Okay, cool, got it.
We don't change the matrix, yeah.
All right. It's past. Let's move on, I would say. But I think it's there have been many questions, and I think it was good that we reviewed this because I really rushed through this last time. Okay, and it's a good basis for going now through vanishing gradient problem because it's also not so straightforward. We can skip all this stuff and start right away with the vanishing gradient problem. And the basic question is, if I'm backpropagating through time, and sorry, this is actually this, I think there was a question in lecture, just this might be confusing now. Why are we calculating actually the gradient of the loss with respect to the hidden state? And this is just like for simplification, because what you eventually want is your gradient of the loss with respect to the weight matrix, as we had just now before. But again, you have to calculate this step in order to get to your weights. Yeah. So you can just ignore that. But we want to calculate the gradient with respect to the weights, but we are now talking just about the gradient with respect to the hidden states. Okay, so anyway, the question is actually what will the gradient be after a couple of time steps? And here we only have 1, 2, 3, 4 time steps. And it's again just an application of the chain rule. So here you see this actually gradient of the loss with respect to this hidden state is the gradient of the loss with respect to this hidden state H2, and then you have the gradient of H2 with respect to H1. And you continue applying this chain rule throughout your sequence. And this is exactly, because if you notice now, our arrows from being like flowing like this through it, they are getting smaller over time. Because essentially what the vanishing gradient problem is, since you apply the chain rule and the same kind of multiplication all over again, if you multiply something by a value smaller than 1 many times, it gets exponentially smaller. And this exactly is the vanishing gradient problem. And in this case, it's actually just 4 steps to visualize it. But usually your sequence is much longer than just 4 steps. And since you're multiplying over and over again by small values, your actually gradients vanish in the way that they get so small that they are not useful anymore for performing any gradient updates. Yeah, exactly.
So
that's
Stefan,
the main idea. Mm-hmm.
Just quickly, I don't mean to take us on a tangent, but will the same conditions hold for the exploding gradient issue also?
Yeah, it's exactly
Okay.
the same
Okay.
same thing. It's
It's
for
just that the values are big. Yeah.
The difference is if you multiply something by a value larger than 1 many times, then your values can explode exponentially.
Okay, thanks.
Yeah. So that's there are 2 problems, actually vanishing gradient and exploding gradient problems, and we will both address both of them in this lecture. Now, a lot of math. I think I went through this twice. It seems a little bit intimidating first, but actually, let's try to get through this. This is our basic RNN equation, right? We actually calculate the new hidden state from the previous hidden state, the current input. Think of this as the embeddings directly, because yeah, you first have your one hot vector and then you get your embeddings, but it's simplified to just reflect the input xt and your bias. Then you apply sigmoid and you get your new hidden state. And now we will not derive this here, but the derivative of ht with respect to ht minus 1 is this expression. Just applying the chain rule to this, we will end up with this here. And now actually what we want to get is the gradient of the loss at time step I. This was before at time step 4, for example, with respect to the hidden state hj on some previous step. So this can be the first one at step like 0, or the first one, the next one, step 1, doesn't matter. But it's important that j is before I in throughout the time steps. Then what we want to calculate is here the derivative of the loss at I with respect to the hidden state at time step j, given some parameters. And how we can actually rewrite this using the chain rule from before. And this, the same thing is then we get our loss with the derivative, the gradient of the loss with respect to the hidden state at time step I, so at the same time step, and then this expression multiplied all over again. So this is actually just rewritten this chain rule. Yeah. And then what you do is you actually just you take this, because here now you have this expression that you have within your product. You take this expression and just put it here. And what becomes clear after you do this, actually what you do is you paste in this expression and then you have your weight here. But since the weight matrix is always the same, we will actually, for I minus j steps, this is the difference between the time step, between the loss and the previous step that we want to calculate the gradients of. And you actually, exactly, you multiply by the weight matrix H this many times. And then if the values in WH are small, this term gets just vanishingly small the further the time steps are getting apart. And if it's large, then it can explode actually as you go further apart between j and I. Let's just move on for a moment because there's some more math. This is more like a proof. And here you have the L2 norms. Actually, I just have a quick reminder here. What is the L2 norm? And actually the L2 norm, for example, for a vector with some content is defined as the square root of the sum of the squares of the values in each dimension of the vector x. Yeah, so it's the square root of the sum of squares. Where were we? Sorry. This is the L2 norm. Yep. And this is just a mathematical rule that the L2 norm on the left-hand side here is smaller or equal than the L2 norm on the right-hand side. And now we get some more math terms actually that are important nevertheless for this definition. And it's actually about eigenvalues. And I looked for quite some time for a nice and easy explanation of eigenvalues. And I found this from a YouTube video. I just will read it. So let A be an n by n matrix. A scalar lambda is called eigenvalue of A, of the matrix A, if there is a non-zero vector x such that the matrix times the eigenvector equals the eigenvalue times the eigenvector. And exactly, this vector is the eigenvector, and the corresponding lambda is the eigenvalue. And just note that there can be multiple eigenvalues for the same matrix and eigenvector, if I'm not wrong. And however, coming back here, if the largest eigenvalue of the weight matrix WH is smaller than 1, then the gradient, actually on the left-hand side here, this gradient will shrink exponentially the more time steps, or the more I and j are apart. And the similar proof, or this is like inverse proof, is actually if you have if the largest eigenvalue is larger than 1. Oh, sorry, I just jumped. If the largest eigenvalue is larger than 1, this leads to exploding gradients, so that your gradients get bigger and bigger and bigger. Is that somehow clear so far? I expect some questions.
Stefan, what does it mean when they say the bound is 1 because we have sigmoid nonlinearity?
So because remember, sigmoid activation function squeezes all the values between 0 and 1. And I guess what this can mean is, since we always squeeze our values between 0 and 1, and we never let the I mean, I didn't really get it why they wrote it here, because this applies to activations, right? So, and I mean, what I think this should say, what I thought this should say, is that since the upper bound of the sigmoid is 1, so you never reach 1 actually, you always kind of will have vanishing gradients. But since since actually the vanishing and exploding gradient problem applies to the weight matrix and not to the activations, I don't really get it why it's written here.
Okay.
Or if somebody has an idea.
I mean, like looking at these two statements, it says like what I infer is you have to have eigenvalue of 1 there. It shouldn't be less than 1, shouldn't be greater than 1, just exactly 1.
Mm-hmm.
That's what I infer.
Mm-hmm. Yeah, well, but in reality, you will be always like above or below, I guess. So, but I don't really get why this what this exactly what this leads to, the bound of this sigmoid nonlinear.
I guess like when in a sigmoid activation function, if you put x to infinity, right, like the maximum value you're going to get is 1. Is that something related to it? Like that's the meaning of bound is 1. Like, so yeah, whatever we supply for x, like that shouldn't exceed 1. So if we put something like yeah, like I guess like whatever value that we pass to the activation function is important. So
yeah,
and I guess that's the bound says like even if you put x as infinity, so we're gonna get the activation function as 1.
mm-hmm. Yeah, exactly. That's a great explanation of what it does. But however, I don't get the relevancy in this context because this is like applied to activations, and the gradient problem is arises from the fact that we multiply weight matrices all over again with eigenvalues larger or smaller than 1. So yeah, I think we know what it means, but not really what it implies for the vanishing gradient problem. But it hasn't been even touched on, I think, in the lecture. So
okay, yeah. I mean, my follow-up question to this was, and we don't need to really get into it, is like, does changing the nonlinearity affect the whole thing? Like, if you change from sigmoid to some other nonlinearity, will the bound change, and because of that, will the conditions that will lead to the exploding or the vanishing gradients change?
Yeah, I don't know.
Yeah,
I honestly don't know what is the effect of the activation functions on the vanishing gradient problems. But if anybody else has an idea, please go ahead.
Well, it's explicit in the equation that we're looking at because you see that it enters into that bound and through that diagonal. Yeah, and I don't know what the sigma prime means. I don't understand what sigma prime is as opposed to sigma, but it isn't a typo because it's in the previous equation as well. But
the derivative of the
it's
sigmoid.
the derivative of the sigmoid.
With respect to what?
It'll have to be that's. I mean, it's the chain rule, and you first have to apply it to the function before you apply it to W and then to H. So it's like you have to start off by applying it. You know, it's like f of z, and you have to do f prime of z before you do differentiate z with respect to x, for example.
Okay,
so it's just an
that's
application of the chain rule.
Yeah, so it does enter into the expression, but as you can see, the part that determines the exploding or vanishing is the matrix norm of WH to the power of I minus J. That's why the matrix, that's why the thing blows up or vanishes. And so my feeling or guess from the equation is that the answer to your question is it doesn't matter if you choose a different nonlinear activation function, you'll get the same result, that it blows up or vanishes.
Yeah.
Okay, thanks.
When you're using sigmoid activations, you're obviously limited to +1 as your maximum. Therefore, if you've got exploding weights, so you get very big weights, all of the weights, the maximum value you can get is 1. As opposed to if you start using like a ReLU, then obviously you have like an unbounded maximum value, and so the non-linearity you choose does influence how, definitely in the exploding gradients problem, what will happen.
But
it's a derivative. It's not, you know, the activation function enters as a derivative. So
and
yeah.
If your weights increase a lot, then all of your neurons, they all max out, they all overload at 1, and there's nothing they can do. Like so all of your signals effectively disappear as they pass through the network and the forward pass.
I don't know, honestly, like really what is the bound? I mean, I get it, the bound on the activations, but still I don't understand, because it you know, it doesn't bind, the bound doesn't apply to the weight matrix, to weights in the weight matrix WH. And as Joseph said, it's like this is the source of the problem, right? Okay, but maybe we have to settle for the fact that we don't really know. That probably the activations can play a role, but we don't really know how. The activation function, sorry.
I guess isn't that what? Sorry.
I think that, well, mathematically these things never, I think, really go to 0. But in computers we have fixed point math. So in fact, these things vanish to zero because the problems we have or the limitations we have on computer. So I think this thing you say that if you have things that are less than 1 and multiplying them one and another, you will get lower and lower values near to 0. And in computer, you will get 0, so you will lose that information. And obviously, on the other side, if it is more than 1, you will explode your floating point limits on the upper side, or maybe more precision issues. So I think these limits are not for, well, they can be understood more if we take that side of the computers, because this thing is never goes to infinity or never goes to 0.
Yeah, that's actually a great point. Additionally, I'm not sure it answers our question about the upper and lower bound of the sigmoid, the upper bound of the sigmoid. But I think this is nicely shown in the draft of the Fast AI book. That this is another problem, and that's exactly what you just mentioned. And this just shows the floating points on a normal computer. And this, if you store large values or very low, like negative values, they are not stored as precise as if you're storing values close to 0, right? And therefore, your gradients won't be as precise as they would be if you're keeping them around 0. So this is another problem of this exploding and vanishing gradient issue. Yeah. All right. So let's move on. Still a lot to get through. And this is now, first of all, this was what is actually the vanishing gradient problem, and now why is it even a problem? And I think by itself, it's already a problem because simply the gradients get smaller over time, yeah? And the gradient signal that arrives here at the end, this is very simplified. So please imagine a longer sequence through time here. But if the gradients that apply at the beginning of the sequence, that arrive at the beginning of the sequence, will be so small that they will not lead to any significant weight updates. So you're really not really learning from the earlier at the earlier layers. And this is already, I think, a problem by itself. And then additionally, if you have some other signal, because remember, you don't always have to have a loss just at the end of your sequence. You can also have a loss at every step. And if this is the case, then the loss of this actually closer step, will be at a gradient of this closer step will be much stronger. And then you will actually, the weight matrix from this step will learn a lot more with respect to this, let's say the short-term context than the long-term context. And that's exactly why normal, like standard vanilla RNNs mostly actually learn short-term connections or short-term context, and not really more than a couple of steps. Yeah, so model weights are only updated with respect to near effects and not the long-term effects. So it's not learning any long-term dependencies.
But is that always the case? I mean, this is just an assumption, right? That the nearest one is the one with like a slightly larger gradient than the farthest one. Like suppose if the case was that H4 was actually the largest gradient signal and the rest of them were small, then the far effect would hold.
Yeah, exactly. It can be that you don't, and sometimes you want to capture a short-term context, right? But I think this is even on the next chart. It's the problem that you cannot tell if there is no dependency on the long term between t and t plus n. Let's say now t we have here and t plus n is here at the end. So you cannot tell if there's no dependency, which is what you're saying, that you actually have only the short-term dependency that makes sense in this case. and the long-term dependency is not something you want to learn. But you cannot tell the difference if this is the case, or if just because of the technical issue of having the vanishing gradient problem, you're actually having the wrong, you're having the wrong gradients. You have a weak gradient signal.
Yeah.
So you don't know if the weak gradient signal should be weak, or if it shouldn't be weak, but actually is weak. And that's the problem also, that you cannot tell these two cases apart.
Yeah.
Yeah. Somehow we just jumped, sorry, to the end, but we're not that far. Yeah, okay, so we've been here, sorry for that. And now we can see just some examples of vanishing gradient. So you have a longer text, and some basically quite at the beginning, it is mentioned that there were tickets when she tried to print her tickets, and there's some text, and then in the end, she finally printed her tickets. So if you see that text, you would predict tickets. But this is already quite some long-term dependency, because you need to remember the dependency actually from tickets all the way to the end of the sentence, or actually sequence here. It goes over more sentences. And in a standard RNN, this won't be actually possible, because these are, I don't know how many steps, but usually 6 or 7 steps. After 6 or 7 steps, the gradient signal fades out. I guess it also depends on the problem, but exactly. And if the gradients are small, then you cannot learn such a long-term dependency. And you cannot actually, the model doesn't remember that she went to print her tickets. So she finally printed her, and then whatever the model thinks is most probable here, but it doesn't really remember that it was in fact tickets. Another example is this here, the writer of the books is or are, and here obviously the right answer is, and there's the difference between syntactic recency, which is like the writer is actually, from a syntactic point of view, the closest word. So you obviously would write, from this perspective, you would write the writer is, but from the just sequential recency, it's just which word came before the gap, yeah? And in this case, it's books, and the model is probabilistic, and just learns books is plural, so I need to apply are, so it will predict books are, even though maybe it's not the best example, because this sequence is super short, so probably the RNN could pick it up even from here. But somehow it's here, there's mentioned that because of the vanishing gradient problem, RNNs are better at learning this kind of sequential recency than the syntactic recency. Exactly, and this just shows again like some reminder of, oh no, actually this goes into the exploding gradient problem. So this is the opposite. If the gradient gets very, very big, you perform actually a very strong parameter update. This can then lead to even parameter updates to infinity, and then you get activations of infinity and infinity losses, and then you actually, your model is broken. But there's a quite simple solution to it, and it's kind of a hack. It's called gradient clipping, and you simply set some rule that, for example, your gradients shouldn't be larger than 5 or smaller than -5. And what you just do, it's like a simple algorithm. You take g hat is the gradient, and you actually, let's say g hat is -7. This is the gradient, it's -7. Your threshold is 5. So the norm of g of -7 is 7. It's larger than the threshold of 5. Then we enter this if statement. And now we are taking actually, we are dividing the threshold 5 by the norm, which is 7, and times the original value -7. And then actually the 7s cancel out, and what you're left is -5. So essentially you clipped your gradient from -7 to -5, because you just don't allow gradients larger than -5, larger than 5 or smaller than -5. And the idea is that you obviously walk into the same direction than your original gradient, but you just take a smaller step. You're more careful. You don't trust the model when it suggests to go very, very large steps. And exactly what shows this nicely is actually this loss surface. And this is very highly simplified because in this case, we don't have any vectors. We just have W is one value and B also. And so you can plot it in the three-dimensional graph here together with the loss. And in this case, you want to go actually down here, the slope, and you perform small gradient updates. But then actually you want to go closer here into this valley towards your optimum, but actually your step is too big, so you overshoot and you end up here. Your loss increased a lot. And then since here, actually your gradient is super steep, you can shoot off somewhere completely else, and you need to go basically all the way back to the minimum. And the idea of clipping is that you simply, you don't allow such updates. You cut it off here, and then it will eventually like climb back down. So it's really just a hack rather than any, but it's quite an efficient solution, I believe. So usually I think it's always part of the toolbox. Exactly, and I think this is just the motivation that, exactly, because finally the baseline is that because of the vanishing gradient problem, the RNNs cannot really learn information, or they cannot really learn to keep information over many time steps. But we want to achieve that, and so we need a different architecture. And this leads us to the LSTM network, long short-term memory. And this is like a specific type of RNN architecture, which was introduced by Jürgen Schmidhuber and his student Sepp Hochreiter, I think at the Technical University of Munich in 1997, as a solution explicitly to the vanishing gradient problem. Because while theoretically RNNs should be able to learn actually from time steps far away, it in practically cannot. So they introduced this LSTM. And the main idea is that we have two separate states, a hidden state and a cell state. And the hidden state we already know from the normal vanilla RNN, but the cell state is new. And I think actually in the TWIML podcast, Jürgen Schmidhuber really nicely explains it. And the idea was basically to add what is the simplest connection that you can add to the RNN. And it's actually an identity connection, so that you just pass from each time step to the next. You always keep passing this cell state over and over again, and you don't do any modification to this. In this case, the information could just flow from the beginning of the sequence completely to the end of the sequence. And also the gradient signal can completely backpropagate in the other direction. But of course, you don't want to just add the identity connection. You actually allow the model to interact with the cell state. And the LSTMs do that actually in a form of like different gates. And these gates allow the LSTM to actually erase information from the state, to write new information into the state, and finally to read information from that state as well at every time step. And these gates can be thought of as actually kind of as mini RNNs within one LSTM cell that regulate the flow of information between cell state and hidden state, or the cell. And these gates can be open or closed. So it's really just, do you let information through or not? And also, this is important, they're dynamic. So they are learned, and they're not like hard-coded to always be the same. They are learned and can change through the time steps. And I think actually before we go through this very math-heavy slide, let's move on to a great blog post, because otherwise I think it can get a little bit confusing. So this is an awesome blog post. It's called The Illustrated Guide to LSTMs and GRUs by Michael Fye. And it goes step by step through all these gates. And I think this will be much clearer. It will be much clearer when we look at the equations afterwards. Here's just some motivation. And yeah. So exactly. Let's look for, first of all, in the RNN, you have, just the cell we basically loop through the cell and pass input at each step to it. So this is like, just we loop through different cells, and now we look into the content of one cell, because the innovation of the LSTM is basically that it changes the content within the cell or the functionality. This is the cell within a simple RNN. Yeah, you get your previous hidden state from t-1, and your input, which is like from the word embeddings from t. Then they are actually combined, in some way concatenated, but actually they're added up in the equations that we saw, and passed through a sigmoid, and then passed on to the next time step. And optionally, you pass on the hidden state out here to generate some output to make a prediction in a language model, for example. Exactly. So this is a classical RNN. This is just a review of the 10H activation function. With whatever values come into it, it spits out, it squeezes them between 1 and -1. Actually, since I do not see the chat, if there's anything going on that I should be aware of, please mention it. Yeah. Okay, so as you can see, without the 10, this is just a motivation for 10H. I think it's not so interesting in this case for us. It's something everybody can go through it themselves. And you see, for an LSTM, actually quite a lot more is going on within a cell. So you have, just like the terminology, red are sigmoids. Actually, I said it wrong up there. Sorry, this is a 10H, obviously, in a RNN cell. It's not a sigmoid. Oh, sorry, too far. Yeah, so you have sigmoid activation functions. You have element-wise multiplications and additions, and you have 10H functions. That's all you have, and some connections between them, and we'll go through them step by step now. Sigmoid squeezes values between 0 and 1. We all know that. And now we go through the gates. Actually, we skipped one. Yeah. So the first is actually called the input gate. And actually, I'm thinking maybe it's the best way to go through these visualizations and then look at the equations step by step. So what's happening with the, actually, before we start, our inputs are the cell state. This is the memory now, the newly added memory of the network from t-1, the hidden state from t-1, and the current input at time step t. And this is the, this is called the forget gate, because you pass in your values that you get from your hidden state and your current input into a sigmoid function and get a vector that has the same length as the memory state with values between 0s and 1s. Okay, so in terms of, like in math, it's this. This is the first equation. You get your hidden state, you get your current input, you add a bias, do some matrix multiplication, and you put it all through a sigmoid, and then you get a vector with values between 0s and 1s. And here it's described as the forget gate. What controls actually what is kept or forgotten from the previous cell state. Okay. So sorry, where's the, yeah. Exactly. So at this step, you get your vector with 0s and 1s, and then you multiply it element-wise with the previous cell step, and then you can forget, for example, the values that are 0, they actually can forget the values that, can you actually still hear me?
Yep.
Yes.
Because I have problems sometimes with a microphone, and I just saw the chat is pretty busy, so I just wasn't sure if you still can hear me. But okay, so I'm going on. I'm continuing. Then you have your vector from the forget gate with 0s and 1s, and you actually forget elements or you keep elements from your cell state, from the memory. Okay. Let's move on to the input gate. You take the same input as before, and you pass it to the input gate. You get another vector with like values close to 0, between 0 and 1. That should tell you which parts of the cell state you will update. Yeah. And then you take the same inputs again and calculate with a 10H function a candidate of update values. And And then what you do is actually you multiply the input gate, the vector of values between 0 and 1, with the candidate values, element-wise, to again, you can keep or discard some of these values. And then you add all these candidate values that made it actually through this input gate, you add them element-wise to the cell state. So through this operation, new information from the previous hidden state, but more importantly, actually, from the current input is flowing into the cell state. But only relevant information is being added, not all the information. So it acts kind of like a filter to what you want to add to your cell state. And let's go back to the math. Your input gate has actually exactly the same form as the forget gate. They all do, the output gate as well. Just takes the same input, has different weight matrices. This is important because you obviously want to learn different weights for deciding what to forget and what to update. But it returns this vector of values between 0 and 1. And then the candidate I was talking about is called here new cell content. And it's C tilde. And it's again, actually the same form. You pass to it your hidden state, your input, do some matrix multiplication, and put it through a 10H. Because you, obviously, when you have some values in your memory, you want to be able to actually make them smaller. So you want to allow the candidate to subtract values from your memory. So therefore you have the 10H here. And this is how it's actually then combined. You have your previous cell state. This we did already this step. So here you apply your forget gate to the previous cell state. So you decide what to forget from it. And then you add to this, the input gate is again values between 0 and 1 that decide what elements of the cell state get updated. You multiply this element-wise with your candidate values, and then you get the new cell state. Okay. And then finally, you get another, you calculate another gate, which is actually next in the cell state. Sorry, the cell state we did already. Yeah, here you just see how it actually gets combined. You calculate these two gates and the candidate value. You forget stuff, and then you filter what you want to update, and you add this, and then you have your new cell state. Yeah. And then we also want to get a new hidden state, and for this we need to calculate one more gate, which is called the output gate. And here the inputs are passed again into sigmoid. We get again the vector with values between 0s and 1s. And now we actually take the new cell state and apply a 10H to it, as you can see. Then you multiply them element-wise as usual to decide what you actually want to pass, into the new hidden state before you create the new hidden state. Yeah. And the equation for this is simply, again, the same gate, same stuff applies. And then you actually get the new hidden state by multiplying element-wise this output gate with 10H of the new cell state. Exactly. And yeah, again, just the difference between the hidden state and the cell state is mainly that the hidden state, or the cell state, is actually, I think we're at the end of this nice visualizations. I really recommend to go through this entire blog post. It's pretty nice, nicely visualized, and there's also a video with it. But actually, the important distinction is that, I just want to repeat this, the cell state is the memory that carries information along, and the hidden state is the internal state of the cell that is used also, importantly, for the prediction. If you're making a prediction at this step, the hidden state flows out of this. So you make your prediction from the hidden state, not from the cell state. And how does this solve the vanishing gradient problem? You can see that actually the cell state has relatively few interactions. Yeah, most of the interactions are done here with all the matrix multiplications are done with the hidden state and the input, and that's where you will also do all your gradient calculations, but there are relatively few interactions here along this line. So you can actually imagine the cell state really that's being able to transfer relevant information from the beginning of the sequence all the way to the end. And also then the gradients can flow like more freely backwards through the time steps. Yeah, exactly. And finally, yeah, exactly. Just one thing I wanted to mention is that there was like a question in the lecture why we are actually not looking when we calculate all these gates, right? Why are we not looking at information from the previous cell state? There are versions of actually LSTMs that do that, and it's in Chris Ola's blog post, for example, and it's called peephole connections. So what you do is simply you add to your input of calculating these gates, you add your previous cell state as well. Yeah, or actually for the output gate, the current cell state. But I think in the normal version or in the standard LSTM, the hidden state, the cell state is kind of reflected in the hidden state, because you actually calculate. You have to think actually the hidden state, how the hidden state flows through the network. It actually flows through here. Then values gets updated. It gets added. Parts of it get added to the cell state, and then it's going back like this. Yeah. So it's heavily, let's say, modified, but somehow signal probably gets through from the cell state, obviously, to the hidden state. Yeah. All right. Yeah, exactly. I just thought I will go through the blog post rather than these, but are there any questions?
Hey, Stefan, I'm trying to understand like the function of how the sigmoid versus tanh, like how they affect this, like or a simple way to put it is, why is it not all tanh? Sorry, I got a little lost in the.
No, it's a great question. Like it's important. This is a very important point, I think. The sigmoid controls the sigmoid is used for the calculation of the gates, right? And what you want your gates to be between 0 and 1, because 1 means pass information through, and 0 means don't pass that information through. Yeah. So when you apply this gate to the forget gate, all the 1s actually let the information from the previous cell state through, and all the 0s or everything that's close to 0 will be forgotten. So you want just this gate functionality, and the gate usually is values between 0 and 1, and that's why you have.
So these are discrete or continuous?
No, they are not discrete. I always say 0 and 1, but they are sigmoid, so they are actually continuous values between 0 and 1, and never 0 and 1.
Right. Yeah.
Just close to 0 and close to 1.
Okay.
And
so I mean, sorry. Would that mean there is a threshold for it to understand its pass or block?
Yeah, exactly. It's just for understanding that in most of the explanations, it says think of it as being open or closed, one or 0, but in reality, it's never completely open or completely closed. Yeah,
okay, cool.
And the tanh, on the other hand, because as I said, you want to be able to not only add stuff to increase your values in your cell state, but you also want to be able to subtract values from your cell state. And that's why you want a tanh that is between 1 and -1.
Okay, brilliant. Thanks a lot.
Okay. Yeah. I think we're good with the time. So I made one step actually just for myself. I wanted to draw this live in the lecture, but I'm very bad with drawing with a mouse and don't have the pen. So it got messy. And what helped me a lot actually is just to take a piece of paper, take some values, and calculate through this entire thing. So I hope it's not confusing you more than it's explaining, but since it helped me, I will maybe go through it. So just some example values, and actually I just drew this up 10 minutes before the lecture because I want to do it live and figure out I'm very bad at it. So actually I figured I should have chosen different values, but never mind. Let's just use what's here. You have your previous cell state and your current input. And just for simplicity reasons, the input is like a combination of hidden state from the previous, because otherwise it would get too messy, from the previous time step and the current input, okay? So this is the combined already the previous hidden state and the current input. And this is the calculation of the forget gate. And it's, again, it's very simplified. And I did it on purpose with zeros and ones because otherwise it gets too confusing, and it nicely shows the functionality of these gates at least, yeah? So you combine actually, sorry, I see it because I made it too fast. I made a mistake on it because it doesn't come obviously from the cell state, but from the hidden state. So I don't want to confuse you. I will skip that part. Yeah, because it goes completely through it. Yeah, sorry for that. That's my mistake.
So Stefan, you mean you want to have x of t and c of t minus 1, and as well as h of t minus 1.
Exactly. I should have added the h of t minus 1 separately. Yeah. But like this, it will be just confusing. So I'd rather not show it. But I think it's just this for, you know, I heard watched many lectures with LSTMs and so on. And for me, this really was the final moment where I really got it, to just draw it out to see, you know, what are actually these gates doing. And then it's quite easy to understand actually. So I just recommend this, but I will not. Yeah, it will be just confusing. Sorry for that.
Okay. Can you share this? It is really cool. I really like it.
Yeah. I will clean it. I will correct it, clean it up, and we'll share it definitely. But it might take me some days. Okay.
Thank you. I appreciate it.
You're welcome.
I have a question. There's nothing magical about sigmoid or tanh. It's just from 0 and 1 or from -1 to 1. So in theory, you can use sigmoid minus 1/2 or 2 times sigmoid minus 1 instead of tanh, right?
Mm-hmm. And actually, isn't that even? I think I may have even heard that 2 times sigmoid minus 1 is even tanh. Isn't it? Because it's like twice as wide on the y-axis, and then you just move it so that you actually, you know, you would basically extend sigmoid on the y-axis up to 2, and then you just shift it over by minus 1, shift it down by 1, so you end up with tanh. So I think 2 times sigmoid minus 1 is even tanh.
Oh, okay.
Okay. So then, if there are no other questions, let's move on. And exactly, so this is just a summary here, why it makes it easier for the RNN to preserve information over many time steps, because we have this separate cell state. And exactly, if you would think that the forget gate is always set to remember everything, yeah, and you never forget anything, then you could preserve information from the beginning of your sequence perfectly till the end. But that's usually not what you want to do, because you want to forget parts of the cell state along the way. And exactly, and it's like for the normal RNN, for the vanilla RNN, it's just harder to preserve that information, because at every step, you know, you don't have a separate cell state and a hidden state. So at every step, you modify your hidden state, and you don't really have this separate entity to that can act as a memory. So there are basically too many interactions to keep the information from flowing. And it's that the architecture is like super simple of a normal vanilla RNN, but it's probably like for practical reasons too simple to be efficient. And then also important remark, the LSTM architecture doesn't guarantee that there are no vanishing or exploding gradients, but it makes it a lot better. And basically all state-of-the-art LSTM architectures, RNN applications are LSTMs or variants of it that we will look into shortly. Oh yeah, exactly. And this is here in actually as late as 2013 till 2015, even though they were around since the end of the 90s, LSTMs started achieving state-of-the-art results in speech recognition and here machine translation, and became actually the dominant approach in sequence modeling. But actually, since things are moving fast, especially in NLP now, the most dominant approach for nearly all NLP tasks are actually transformer models that we will learn about later. And here you can just see that, in terms of popularity, if you just check the content of machine learning conferences or NLP conferences, you will now much more often hear or find the word transformer than RNN, which leads again to the fact that maybe to some degree it can be harmful to just pursue one direction. This is like Stephen Merity's point, to just pursue one direction in this sense, transformers, and completely neglect or kind of ignore RNNs and not further look into them. But transformers are very powerful. Okay, and now we're getting to some different LSTM architectures. And the one we're going to look at is called gated recurrent unit. It's from 2014, so quite much newer. And actually, there are many different LSTM architectures. So before we just saw these peephole connections, and there are many different variants where researchers try to add some gates, to modify gates, or to remove gates. And even the researchers, there was research comparing different RNN architectures for different tasks. And the main result is actually that it doesn't really matter which exact architecture you take. Most of the cases lead to similar results. And also there is not really one architecture that performs consistently better on all tasks. So it depends really on the problem at hand, which kind of architecture you want to use. So I think one interesting thing that I picked again up from the Schmidt-Huber podcast is the idea of evolutionary LSTMs, where you actually allow the learning algorithm to modify the architecture. And through this, or parts of the architecture, not the entire architecture, right, but parts of the architecture. But anyway, I think the most popular alternative of the LSTM is a GRU. And it also, it's slightly simpler, but I find it somehow less intuitive, at least for me, because it mixes up these, in the LSTM, you have these nicely separated gates, and they are quite intuitive in what they do, but in GRUs, they're kind of merged, so it's a little bit harder to, I think, or at least in my case, it was harder to understand it. And also, we don't have nice visualizations, so we have to go through this here. Yeah, because most blog posts on LSTMs and GRUs are actually explaining LSTMs in depth and then saying, okay, and there are also GRUs and you should look at them as well. So we're gonna do something similar. So the main difference is you get, again, actually the thing that made LSTMs so effective in remembering long-term dependencies, the cell state, you get rid of this again. And you wanna do the same thing, you wanna achieve the same goal, solving the vanishing gradient problem with actually just a hidden state, but you have some gates. And exactly, and you have two gates that are a little bit confusing also, but let's try to clear it up. So you have an update gate, and this kind of combines the forget gate and the input gate. And just do it. So we don't even have a picture here. So I see something blinking here all the time, so probably the chat is very busy. Please, if you want to discuss something, you can also speak up. I think we have still some time. Yeah, so this is a GRU unit, and you have only these two gates. So you have the update gate and the reset gate. And we're going to look at them. Let's look at the math first. So the input is again the same. You just get the previous hidden state and the current input, and you have some weight matrices and a bias. You put them through a sigmoid and get some values between 0 and 1. And the update gate combines the forget gate and the input gate, kind of, but not really in a perfect way, but more like in a rough way. It's not really a perfect substitute for input, for forget and input gate, but it performs similar functions. And exactly. And the reset gate, on the other hand, controls what parts of the previous hidden state are used to compute the new content or the content of the new hidden state. And I think it gets clearer when we look at this. And the reset gate. So first you calculate a candidate for the new hidden state, h tilde, and then you calculate the new hidden state. Yeah. And the update gate is performed, the update gate is used for calculating the new hidden state, and the reset gate is used for calculating the candidate. And I think that's the best distinction, maybe, because the new here, what is called new hidden state content, is this candidate value, or the candidate content is a vector of candidate values in fact. And again, it has inputs xt, then the previous hidden state, but also you multiply already here with the reset gate, element wise. Yeah, so here you have the chance of forgetting stuff again when you calculate your candidate. So this is actually the forget gate, but in context of calculating a candidate. And then you have your candidate, and you multiply it element wise by the update gate. So here you have, again, zeros, vector with values between 0 and 1. So here you decide which parts, which elements of the hidden state should be updated with the candidate values that you calculated before already. And with 1 minus u, this is just exactly the 1 minus the update gate. You multiply, you take this and multiply it element wise with the previous hidden state. So here you can actually again forget stuff. And this is actually the main difference, because in the LSTM, these functions like forgetting and updating are actually working independently of each other. But here in the GRU, you do either or, yeah? Because it's just 1 minus u, it's not separate gates. So if for example, one element of u would be 1, yeah, then you actually have 1 minus 1, and then you have 0 times the element in the previous hidden state. So you forget, you multiply one element of the previous hidden state by 0, so you forget it. But then actually 1 times the same element, but in the candidate value. So you take exactly this new candidate value and add it to the hidden state. So you can either forget and update, or keep and not update. But again, ones and zeros and ones are, just for explanation here, it's always somewhere in between, right? This is important.
Stefan, you said that the candidate h tilde of t is a set of values. You said it's. I'm wondering about the sizes. Are they still the same size, h of t and h tilde?
Yeah, definitely. It's all the same sizes. Okay. And usually, I think quite common is, for example, 512.
Yeah. Okay.
For LSTMs, or bigger, 1024. But I think quite common is 512.
So when you say a set of possible values, that's what I mean. I'm a little confused about that. Like, is it like just one previous hidden state, or a bunch of previous hidden states? Is it just t minus 1, or?
Yeah. Well, it's t minus 1, but t-1 should reflect the entire sequence.
Okay.
Yeah. So yeah, it's only from one time step before, but it should reflect everything that came before, and especially, and exactly this mechanism of these gates should allow the network to regulate how to modify this state over time. You know, and when you think some parts of my hidden state from the beginning are actually super important for the end, then I want to keep them and I don't want to modify them. And others, actually, they were just maybe useful for some stuff that I did in the beginning, but they will be useless in the end. Then I want to forget them and update them.
So these parts that they refer to are basically individual elements of the vector.
Yeah, exactly.
Okay.
Because the different elements in the hidden state, they can have different functions. Like, for example, I heard some examples somewhere that, you know, part of the hidden state might track if it's plural or if the subject is plural or singular. Yeah. So it stores, okay, current subject of the sentence is singular, but when you get to a new subject, you might want to update that. So you keep that as long as it's useful, but then when you see actually, oh, it's a new subject, I need to update now it's plural. Now I need to actually override this value in the hidden state.
Okay.
Yeah. Okay. And each value in this hidden state can have completely different purposes, right? And functions. And that's really nice. This the blog post by Karpati shows at some looks into some actually elements of hidden states to see what parts what functions they perform, right? It's like I think he said that 95% of the activations are actually not really interpretable and just a mess, and like, or to humans not interpretable, but 5% show some nice behaviors that is interpretable. For example, I remember that there were some activations that actually turned on when you were inside quotations, for example. Yeah, so it keeps track. Okay, I'm inside a quotation, so I need to write some different stuff, and in the end I need to close it again, and stuff like this. Yeah.
Cool, thanks.
All right, more GRU related questions, or can we move on to the comparison? All right. Exactly. So actually, main difference is GRUs are quicker to train because they have less parameters since you have one gate less, and usually they perform similar in terms of accuracy or whatever your metric is. But sometimes LSTMs lead to better performance. So I think here, or the rule of thumb is also you start with an LSTM and then you can see if GRU gives you the same performance, and then you can switch because it's just more efficient to train. All right, now taking a break, I think, from the LSTMs and GRUs and moving to a little higher level. Vanishing gradients and exploding gradients is actually not just a problem of RNNs, but it also turns up in computer vision. For example, you know, you have now some computer vision convolutional neural nets with 150 layers or something like this, and since they obviously don't have the sequential structure, but you have, again, many matrix multiplications all the way from the top of the neural network to the bottom. And so they also can suffer from vanishing or exploding gradient problems. And what is usually, or what was like key innovation here is the what's called ResNet. Fast AI users are familiar with this, and it adds these skip connections. So you have some matrix multiplication activation functions here, but then you add the identity, meaning that you don't just move from X to f of X, where X is this function, but you again just add element-wise the identity, and through this you kind of always jump over a couple of layers, and again make it easier for information to flow from the bottom to the top, and the other way around when doing back propagation. And actually only these skip connections allowed researchers to train large networks effectively. So this is this vanishing or exploding gradient problem is really a problem that was kind of preventing the successful training of deep neural networks, and these innovations coming from ResNet or LSTM should really not be underestimated, because they essentially really allowed us to train deeper and much more powerful models with more data then. There's another variant called the DenseNet, and somehow, I don't know the details of this architecture, but it connects more things to each other. So it adds like these skip connections, not only across a couple of layers, but also from the complete beginning to the end. And yeah. And probably it allows, again, like to train deeper networks. And some highway connections that are the same idea of gates coming from LSTMs applied to ConvNets. Yeah, and yeah, exactly. So also ConvNets or general also feed-forward, standard feed-forward neural networks, if they're deep enough, they can suffer from vanishing or exploding gradient problems. But it especially applies to RNNs apparently because of the sequential structure, that you just loop with the same weight matrix over and over again through the sequence. And this makes, you have like, even though you have the same weight matrix, you essentially, the network has depth across the time axis. And yeah, we looked at this already. It's just a summary.
Hey, Stefan.
Yeah.
Are there choice points between when to use LSTM, when to do GRU?
I guess I'm not aware of any.
Okay.
It's just like, I mean, in Stanford lecture, they recommended LSTMs, right? But because usually you can have a little bit better performance, I think, in more tasks with LSTMs. So they recommend the LSTMs rather than GRUs. Another part might be, for example, in fast AI, the standard RNN architecture is called an AWD LSTM, and that's like just a very well-regulated LSTM architecture. And I'm not sure if something similar exists for GRUs. I guess more research went into LSTMs, but I don't think there is really a clear formula that you should use LSTMs for these use cases and GRUs for others. It's more just trial and error. All right. Now we're approaching the end, and we'll cover bidirectional RNNs and multi-layer RNNs. And exactly, so last lecture we looked at this example of sequence classification, in this case, sentiment classification, where you want to find out the sentiment of a sequence of data, of text. And you get your hidden states in the RNN, can be an LSTM or whatever, but you get your hidden states and then you accumulate them. Either you can just take the last one, or you take an element-wise mean or maximum to get a sentence encoding. And from this you predict then if the sentence is positive or negative, or any other task of text classification. And this hidden state can be seen as a contextual representation of the word terribly in this case, because it also is aware of the stuff that happened before. But since we are actually moving from left to right sequentially, looping through the sequence, it's not really aware of what happens to the right. So it's a contextual representation of terribly within the sequence to the left. Yeah. But it actually might be important for the representation at this time step to be aware of the words that come after it. So in this sense, we are missing out of information that could be reflected in this hidden state. If we could look to the right, that could be helpful for this prediction, but we cannot use this information because we are not aware this even exists actually. And especially, I think this terribly was an example here, because terrible can be usually negative, but terribly exciting is actually very, very positive. And the solution to this are bidirectional RNNs. And this looks a little bit complicated, but it's actually not. it means that you perform this is your standard forward RNN. This is what we discussed all the time. You go through your sequence from left to right. And additionally, you do exactly the same thing from right to left. Yeah. So you process your inputs just not from the first token in the sequence to the last token, but from the last token to the first token. And then you have actually for each step, you have two contextual representations. And then you combine them using concatenation. And then you have your hidden states that are concatenated, but they can contain contextual information from both the left and the right. And for many tasks, this is actually quite helpful, as you can, as is quite intuitive. And this is just the math notation. Exactly here, you compute a forward RNN with the previous time steps going from left to right, and then you compute at the same time, usually, a backward RNN going the other direction from t+1, like going backwards the other direction, and then you get your final hidden states. Yeah, from the hidden states, from concatenating the hidden states from both directions. Yeah, exactly, and it's important that I think here's generally, but in most cases, these RNNs have separate weights that you want to learn separately. And this is just a simplified representation, just not to have so many arrows, but it means exactly the same. And these are then your concatenated hidden states. And then it's just they are not, these bidirectional RNNs are not applicable to all to all tasks. For example, for sentiment, you can use it because you actually, from the entire sequence, you want to predict the sentiment. But if you want to do language modeling, let's go to the bidirectional RNN. If you want to do actually language modeling and your task is to predict the right word from the left one, you would be cheating if the model could look at both, because you would make your, in the language model, you make your predictions at each time step from the hidden states, and in the bidirectional RNN, your hidden states are actually these concatenated ones, and these contain information from both sides. So in this case, you're actually cheating when you look left and right. So you cannot apply this kind of reasoning to a language model task. Yeah, but there are actually versions. For example, in fast AI, the ULM-fit model that achieved a couple of years ago the state of the art in the IMDb sentiment classification. It's also based on language model pre-training, and how they actually created a bidirectional model, even using language models, is they didn't really create one bidirectional model, but they first trained a left to right language model, then fine-tuned this as a classifier, got some predictions, and then they did the same separately, training a right to left, like a backwards language model, just predicting from right to left, but it's a separate model, so it doesn't cheat. Then you again fine-tune this for as a sentiment classifier, and then you get your predictions, and then you assemble your predictions by just adding them and dividing by 2. And this is a way of even kind of getting bidirectionality into language model, or not. You don't really get the bidirectionality into the language model because they are trained separately, but you use bidirectionality even with language models. And of course, another way how to do that is BERT, the state-of-the-art Google transformer model that has even in the name the word bidirectional. And the main difference, what it does is actually it doesn't predict like GPT-2. GPT-2 is a left-to-right language model, so it is unidirectional. It just goes from left to right. But BERT actually uses what's called masked language modeling, and it kind of hides parts of the input just somewhere, and the model has to predict or fill in these gaps with context from the left and the right. But we will learn, hopefully, more about BERT later in this course. And finally, multi-layer RNNs, or also called stacked RNNs. it's again just adding another dimension next to the time dimension, adding actually another dimension vertically to the RNN, just by adding another layer. And this looks like this. Here, this is, for example, a 3-layer RNN. And it's actually quite a simple idea. So instead of these hidden states going directly making predictions, the hidden state from one layer, from the first layer, is passed as an input to the next layer, and there the output is again passed as an input, and then you make your predictions with the final layer. And then you can exactly have finally to combine all the ideas we've learned in these 2 lectures. You can have actually multi-layer bidirectional RNNs with LSTM cells. And exactly, and also what is important, that you, like, practically, since RNNs have this sequential structure, you're looping always through the sequence. This is actually quite expensive computation, and therefore practically you cannot really have RNNs much deeper than 8 layers. I guess Google's big RNN translation model was like 8 layers. But then you even need to add these skip or dense connections, so some identity connections, I think, additionally to the LSTMs. And what works actually is that these transformer-based networks, that's also why they're so effective, because they got rid of this whole idea of looping through a sequence, and they're processing all the input at once using attention, and add also a lot of skip connections, and therefore you can train these transformer models faster on larger amounts of text, and also using much more layers. So here, actually, this is from 2019. So here the statement was that transformer-based networks can be up to 24 layers. Now, as of, I guess, last month it came out, May or June 2020, we can say that the deepest transformer model is actually GPT-3 with, what was it, 96 layers. And then you can learn much more complex representations of language that can help you then achieve better results than these RNNs. And I think that's it. All right, still somebody there? some questions left? Maybe I'll have a look at the chat.
That was brilliant. Thank you, Stefan.
Thanks. I hope it was helpful.
Very much, yeah.
Thank you so much. Appreciate it.
Welcome.
Great job, Stefan. I wonder if you could add, I know you've done this before, but could you post the link to your GitHub? Because that's a really nice collection of articles and blogs that you've put together. I think it'd be great if you post that to the Slack group. Yeah, definitely. I'll repost it. And maybe in the future, I will even add some small explanations, because now I just added titles and links. And I also really want to work on that, that numerical example that I kind of screwed up. Sorry for that, because it really it helps. I think it becomes quite clear if you just write it down and look at the numbers, how they're changing using these different types of gates. Yeah. Yeah. Good. So thanks everyone, and I think we have a break next week, right? So you can go through LSTM some more if you want, or take holidays. I will take holidays from LSTMs. I can tell you that.
Is anyone aware where RNNs are? This is kind of used other than language models. I saw Stefan, you shared something with protein synthesis, I think, if I'm not wrong. But like, for example, like predicting the next task, like a more, I don't know, like for example, Airbnb, I think, uses it.
Okay.
Like their embeddings are kind of used to kind of share identical location sort of thing, but I'm kind of more of looking for predicting the next task from a user, which is very much like a sequential task, right?
Okay.
You do something on the app, then you do something else, like you order something, put it into your cart, something like that. In that situation, has anyone seen an example or a blog post or an article, something related to that?
I haven't, but it sounds like a great idea, actually. It's probably a hard prediction task, because the the space is so large, users can usually do such a lot of different things in an app.
I'm
But I mean,
pretty
so
aware.
is language modeling, right? So
Right, exactly. I'm pretty aware it's used, but it's some of those things that I'm pretty sure you can't publish a paper. There's no value, but it's something that's used in the industry. But that's why I've not been able to really find something. I was curious if anyone else has seen.
I haven't seen it published for that type of thing, but I've seen it published for time series prediction, obviously, and stock prediction.
Right. Okay.
There's a Kaggle competition about stock prediction, which is actually linked also as well to predicting sentiment from Twitter tweets. And yeah, there's examples in there of using LSTMs for the stock prediction.
Ah, okay.
Could you post a link to that Kaggle competition in the Slack group, maybe?
Yeah, sure. Yeah.
Is it active or an older one?
It just sort of finished. It was like the competition cut off about December or something, but like the winner wasn't being announced. It was meant to be in July because they were going to like do 6 months of predictions to see whose model was the best. But I'm not sure how any models will fare given how the stock market's been recently. So they've probably all done badly. But yeah, I think it's due to sort of actually sort of finish and the winners be announced next month.
And do you know any like, you know, kind of the results or how good LSTMs and RNNs are for stock market prediction, like in, you know, compared to the traditional like time series prediction forecasting tools?
I don't, sorry, no, but as I say, there were several of the notebooks in the Kaggle competition that were using LSTMs for the time series prediction, but I'm not sure if they were amongst the leaders in the competition or not. I don't know.
Interesting. I also know that LSTMs are also used in reinforcement learning. I think if I'm really not an expert at all on reinforcement learning, but I guess that some variants of reinforcement learning algorithms contain LSTMs to plan the future.
Yeah, I think Schmidrober again wrote a paper on that too, the world model one, which is reinforcement learning based. So yes, LSTMs are very much used strongly there.
Yeah. And I think in settings like this, especially where you actually really have, like where you explicitly want the sequential nature, LSTMs definitely will stay relevant, because I cannot imagine how you would, you know, do that with a transformer, because you want the sequentiality.
It's a great presentation, Stefan. Yeah, the application I'm interested in is I think they combined CNN and RNNs for image captioning. So you can say things like, there's a boy on a skateboard, and in the background there is a cat moving around. Right? And so that was around for a few years. Like I think Kalpati and Fei Li had a project on image captioning. Right? But I think the newer one is called Visual QA. I just put a blog, VQA. So it's like they even created a huge data set about open-ended questions about images. And, you know, so you basically have this incredible combination of CNN and RNN. Yeah, I'm not an expert, but I saw this at, I think, ICLR or one of the conferences. So it's crazy. Then you can just sort of ask any sorts of like have a question answer session with the images.
Yeah.
Like who's wearing glasses.
Okay.
Yeah.
That sounds very impressive. Yeah, I was just aware of the classic image captioning, right? That you, because in the Karpati lecture, it's actually, so what you do is or I mean, at least for the image captioning, is you have a separate CNN model to process the image, and then your output, you take your last layer from the CNN, and through that, or with that, you initialize the first hidden state in your RNN to produce the text.
I see.
And that's how you create this connection between the CNN and the RNN. So you first encode your image, and then you give that to your RNN and say, now go and produce a sentence of text.
I see. Okay.
Yeah.
Yeah, I think one of Fei Lee's students now, he's a professor and he started like more work on this combining, extending this ideas further. Yeah, I'll try and see if I can find a link and post it in the chat.
Yeah, that's interesting. All right, so I think we're nearly out of time. Finally, we took nearly two hours. But I guess I'll stop sharing. And I think if nobody has any more questions, then we can end the session.
Thanks, Stefan.
Yeah,
Cheers.
you're welcome.
Thanks very much. That was really good.
Thanks.
Glad to
Stefan.
hear. Okay. All right. So I'm also taking off. Bye, everyone.